Welcome at the third of this year's Kaiser Spring Lecture with the overall theme Back to the Moon. Since we're celebrating the 50th anniversary of the moon landing this year. The last 2 weeks we looked back at the history of lunar exploration and we learned how the moon itself as a giant particle detector. Well, this week we're going to look a bit further into space at moons beyond our solar system. And our speaker of today, Dr. Matthew Kenworthy, he did his PhD back at the University of Cambridge on astronomical instrumentation, a topic that has kept him interested for ever since. And well, after several other activities, he moved to Leiden in 2010, and where he is now an associate professor and leading some very interesting research on extrasolar planets. And he's always looking for new methods to detect these hard to see extrasolar planets. Please welcome Dr. Matthew Kenworthy.
Thank you very much, Kira, for a lovely introduction, and thank you all for turning up this afternoon. I'm honoured to be giving this talk today. So, you've been hearing about the moon in our solar system. I'm going to tell you about how we're trying to find moons in other stellar systems near and far. So I thought I'd start off with one of my favourite photos from moons in our solar system. So this is the moon in Enceladus going around Saturn. What you're seeing here are the rings of Saturn almost edge on. Cassini was this camera sent up by NASA, and it flew around Saturn for about 10 years, and a couple of years ago they plunged it into the atmosphere deliberately. But one of the discoveries was on the moon of Enceladus, at the South Pole, there are jets of material being thrown out. So the inside of Enceladus is being squeezed by tidal forces, and there are cracks in the southern pole region, and it's material which is freezing, and you can see these little fingers are scattered like that. And that's really part of the stepping stone as to why we're interested in exomoons. So what this is a picture of the solar system as we're looking a long way away, looking back with the sun in the middle, and all the interior planets, the terrestrial planets, Mercury through Mars and Ceres in there. The big search for NASA and other big space agencies is that they ultimately want to find life on other rocky worlds around us in the galaxy, because we think it should be a fairly common thing. But the trouble is, part of my research was to try and build optical lenses so that we can take pictures of planets around nearby stars at exactly the right distance. So there's a magical Goldilocks zone called the habitable zone. And this is the distance from any star where you can have a rocky planet and liquid water can exist on the surface of a rocky planet. Because we think liquid water, is very, very important to catalyze a lot of life-bearing reactions and chemistry and biology. So look for somewhere you can see liquid water. And you can see that for us, we're near the inner edge of the habitable zone for the solar system. And Mars used to be a long time ago, but the sun's luminosity changed and so it's moved down. The trouble is, if I go off to a big telescope and try and take a picture of an Earth around a nearby star, it's very, very, very hard because stars shine with light and planets don't. Okay, so what we have to do is rely on the reflected light from the surface of the planet. And for the Earth, in the habitable zone, it's about 1 part in 10,000 million, 1 part in 10 billion. And that's very, very, very difficult to see. So, if you're stretching your head and trying to work out where else do we have liquid water in our solar system? Well, it turns out we have an awful lot of moons. So, for the Earth, we've just got one extremely unusually big moon, but for all the gas giant planets, they all have moons and they all have multiple moons. And a couple of the moons are actually bigger than our moon, and one of them has an atmosphere. Titan has an atmosphere which cloaks its surface. And there are several of these moons which are rocky and also have lots of water surrounding them. They have an undersurface ocean and an icy outer shell. So there's far more opportunities maybe for life to generate on an exomoon instead. There's no good reason why other giant planets in the universe or the nearby or around the nearby stars, there's no reason why they shouldn't have lots of moons as well. So maybe we increase our chances if we try and find where exomoons are. So this prompted several people, but one of them was a professor called David Kipping, who's at the University of Columbia in New York, to look for exomoons with Kepler, and I'll describe the technique in a minute. But basically this is the kind of thing, if you've ever seen the movie Avatar, or if you're older and like me, you watch a lot of Return of the Jedi and you know, the Ewoks on the moon Endor. The idea that you can't live on the gas giant planet, but maybe the gas giant planet has a moon, and the moon can be up to Earth size. There's no reason a priori why you can't have a habitable zone moon orbiting around the planet in the habitable zone of those nearby stars. So David went off and said, right, how can we find exomoons? And so this is one of the first techniques which was really used, but I should describe a bit about the satellite he used called Kepler. So here we have the technique that we used, and to date it has detected the largest number of exoplanets in our galaxy. So it's the transit technique. This is a transit that we saw from Earth. The orbit of Venus is interior to the orbit of Earth, and so every so often the geometry of the orbits line up and we get a transit. And so this is the 2012 transit, and I think we have to wait another 88 years or so until we can see the next transit. But what happens is that as the planet moves between us and the sun, it blocks a tiny amount of light. About 1 part in 1,000 of the light of the star is dimmed. Now, obviously, there are a couple of problems. We've got star spots, we've got sunspots, and they look an awful lot about the same size as Venus, so you have to be careful if you see a dim. But this was the transit technique. And originally, 20 years ago, when people were trying to look for exoplanets, they said, well, there's no chance that we'll see any transit, because if you take the solar system, the big fat planets are a long way from the star. And so most astronomers dismissed this. They said it's a useless method because the chance that you get the orbit of the big fat planet edge onto your line of sight is really tiny. So we totally didn't bother looking, which is a shame because we could have seen these a lot earlier if we bothered to look. So this is what is called a light curve. So what we do is we take a picture with a digital camera every 10 minutes of a bunch of stars in the sky. And so this is time in hours along the bottom. And here's how bright the star is. So normally the star is not blocked by anything, so it's 100%. But in this case, this particular star, 209458b, this was the first transiting planet discovered. And you can see that the light from the star drops by 1%. 1 part in 100 is blocked by the planet as it moves in front of the star. And by measuring this dip and seeing how long the dip lasts, you can work out the orbit of the planet and the size of the planet, which is pretty amazing. Now, of course, you don't see the star and the planet like this. There's no way we can see it. We just see a point of light, just the light from the star. There's no way we can see that shadow, but we see its effect. And in fact, one of these first measurements was done by Dave Charbonneau, and he used a 4-inch telescope. Went out into the back of Harvard University, set it up in the courtyard, and what's beautiful about this technique is you don't need big telescopes. You can do it with small telescopes. Additionally, if the planet, and so what's happened is that we started discovering more and more of these systems from the ground, because you can use small telescopes to look at lots of stars at the same time. And these planets are big fat planets, but they're really close into the star. It takes about 12 years for Jupiter to do 1 lap around the sun. These things take 3 days, and they're much bigger than Jupiter. So nature makes incredibly different planetary systems than the one we're sitting in. So a few scientists were worried. It says, are we the unusual ones? Are we the weirdos with the big fat planets a long way out and the rocky planets tucked in? Or is it this particular technique only spots the big fat planets when they're close to the central star? But here you can actually, with really precise telescopes, you can actually see the phase of the planet as well. We can actually see the light bouncing off the planet at different parts of the orbit. So you see the main transit here, it goes around, main transit here, but you see this gradual brightening and fading over the whole of the orbit. And that's incredible. We're actually seeing like moon phases. So what happened was, because you didn't need a big telescope, after a lot of arguing and wrangling, this satellite was launched, Kepler. So this was in 2009, 10 years ago. And it was pushed out to one of the Lagrange points, And so this is a 1.2 meter diameter telescope. If you had this on the ground, not many professional astronomers would use it. It's not that big. However, when you're in space, you're above the Earth's atmosphere. So that means you can do lots of really cool things, and also you don't have the problems of the Earth's atmosphere ruining your measurements. So Kepler went out, and I'll just show you what, so that's it being launched. So these are the solar cells on the side, and then this is what the satellite looks like. So solar cells on one side, this big tube here, it's basically a giant reflecting primary mirror telescope. So if I chop it in half, this is what you see. There's a primary mirror, and what we have is a huge digital camera. So just like your camera phone's in your pocket, but several tens of thousands times bigger. So this is what they look like. These are all the cameras for Kepler. So it's gigantic. So this takes 92 gigapixel images each shot. And so what Kepler did was they launched it out there, and they stared at a particular patch of sky in Cygnus. And so this is one readout of the Kepler camera, and they took one picture every 30 minutes and just kept on going for 4 years. All day, all night, they don't have to worry about the sun, they stared at the same point and just kept on taking photos, and what they were looking for was that little dip of a few hours which indicated a planet was moving in front of the star. And within a couple of years, they found over 700 candidates. And the original goal of Kepler was to look for the transit of an Earth-sized planet around a solar-type star, so another Earth. Trouble was that one of the wheels, there's a basically gyroscope wheel, and one of the 3 wheels broke down halfway through the mission. So the original mission of Kepler was to measure other Earths transiting sun-like stars, and it completely failed. The side effect was that it was wildly successful at finding tons of other planetary systems in the universe. Wildly successful. It's beaten everything else completely down pat. So it found Earth-sized planets, it's found giant planets, it's found Neptune-sized planets, it found super Earth-sized planets. It sees these transits, and it discovered transiting systems, planets in incredibly eccentric orbits, whickering around their stars in a matter of hours. It found multiple star systems, so multiple planet systems. So this is the orrery. So this is all the Kepler systems done to scale with the solar system. And if this works, yeah, there we go. So you can see the solar system with the orbits to scale. And nature makes tons of completely wacky planetary systems. It's crazy. All of these are real measurements. So there are multiple planet systems, 3, 4, 5, 6 planets all orbiting around each other, all stuffed within the orbit of Mercury. It's crazy. It's just completely bonkers. Nobody expected this. Okay? And it just keeps on going. So this is all to scale, and all the time scales are right. You know, it's I just find it utterly amazing. And this is just by taking pictures. Right. I mean, there are a few technical details and a few $1 billion, but but you can do this. This is absolutely, when I saw this, it blew me away, because I grew up and it was 9 planets, and then it went down to 8 planets, and now it's thousands and thousands of planets, right? There's been a huge change in my life. For some of the younger people here, it was 9 planets for me. So, anyway, this is what Kepler produced, and this was just looking at 200,000 stars in Cygnus. They picked the area so that there were no bright stars which would ruin the camera, and all that kind of stuff. And we've done the same from the ground. One of the most amazing results that we've seen is this is called the TRAPPIST-1 system. So this was discovered 2 years ago. This is a red dwarf. It's a star about a tenth of the weight of the sun. And it's got not 1, but it's got 7 planets all orbiting around the star. And this here is the light curve. This is measured from the Spitzer telescope, but we discovered it on the ground with a 1 meter telescope. The astronomer who saw this couldn't believe his luck. Right? So you get A, B, C, D, E, F, G for all these planets. And several of these planets are in the habitable zone for this star. So there's a lot of excitement at the moment is, you know, could we have water existing on the surface of these planets? And there are good reasons why not, but I'm not going to talk about that today. But it's just a cool discovery. When I saw this, I thought, okay, this is crazy. Anyway, so it turns out those transits are regular like clockwork. It's like tick, 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 tick. So here's an animation. And so we're seeing the transits, and the planet transits very, very regularly. Every orbit is exactly the same length of time between the previous orbits. So you can see the little clock there. Ding. And one planet on its own has a very regular clock. Okay. All good. But now, what happens if we put a second planet which doesn't transit in the system? That second planet tugs at that first planet. Sometimes it pulls it faster, sometimes it slows it down. So now we'll watch the transit with the effect of that second unseen planet in it. And the timing's no longer regular. It's not tick, 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 tick. It's tick, 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 tick. And even though that second planet doesn't transit in front of the star, we can work out that it must be there. Something must be there speeding up and pulling down the planet which does transit. And so this is one of the ways we can also look for exomoons. So we use that method to measure the weight of planets. So what we have is, if we now have a planet and a moon, and they orbit around each other, okay, the planet doesn't stay still. The planet wobbles backwards and forwards a little bit as the moon orbits around it. So sometimes the moon comes first, and then the planet is trailing it just by random chance. And then other times, if you watch a few transits later, the planet leads the moon. Now the moon's too small for us to detect the drop in light, but we can still see the planet, we can still see the big fat planet. So what happens is that the centre of gravity with this white dot, that centre of gravity dot is keeping the regular time, but we see the black disk only, because it's much, much bigger than the disk of the moon. And it's called transit timing variation. Very silly phrase, but it's quite accurate. So with Kepler, David Kipping and his team said, right, we've got 1,000, 2,000 transiting planets. Let's take the best sets of planets which could have moons around them, and we'll look for transit timing variations. We'll measure ultra precisely that wiggle as the planets either speed up or slow down as the moon's orbiting around them. So all the grey dots are all the planets detected by Kepler. And you can see this is the length year of the planet, so going from one day up to the Earth would be here, 365 days, and how big the size of the planet is in Earths. And you can see there's a huge number of small planets at very small distances around stars. We know we're not seeing all of them because it's just random chance whether we see an orbit edge on or not. So this is a very strong lower number to the actual number of planets in the galaxy. But we can work it out, we can sort of work out what we're missing and add up all those numbers. So Alex Tichy, his graduate student, and David Kipping went off, looked at these 284 gas giants, and I think I'm pretty good with mathematics, but it turns out David and his graduate student are much, 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 much better at mathematics than I am, and they did this incredible piece of work where they looked at the light curves for all those planets and said, do we see that little wiggle backwards and forwards? And it turns out no. So this was a huge piece of work, took about 6 years to do, lots of computer time. They couldn't find a Galilean system. So if you started with Jupiter, with the 4 moons of Jupiter called the Galilean system, they said they could have detected it. So if one of these Jupiters in Kepler had a set of exomoons, they'd have seen them. They could add in fake moon signals, and it turns out the data was good enough to see it. So they were pretty upset about this. I mean, they're very nice about it, but they were clearly like, oh, I should have seen it. But they just did an incredible piece of work. Each time I look at it, I go, wow, I don't have the head to do that properly. So they were getting to the end of the project, and they saw this system. One of the stars is called Kepler 1625b. So this is a super Jupiter which is orbiting around a star. The orbit's about 2.5 years to go around. And then they saw something weird was happening with the light curve. So first of all, this is the light curve. So this is the planet moving in front of the star. But if you notice, there's this weird kind of little shoulder on either side of the main transit. So there's big fat planets transiting the star. But every orbit the curve looks very slightly different. Now the trouble is, if you have to wait 2.5 years for the planet to orbit around, that means this is at least 6 years worth of data. And they had to use the Hubble Space Telescope at exactly the right time to see this eclipse happen again. And what they spotted is, we think, the first exomoon system. But it's weird. Always, the first thing you find is always weird. Okay, it's the tip of the iceberg, you always find it. So what it seems to be is that there's a gas giant, or one of them, we've seen lots of gas giants, but it also seems to have a moon, and the moon is much, much, much bigger than we'd expect. The difference in weight between Jupiter and its moons is about 1 part in 1,000. This is a big fat moon. It's a weird moon. It's the size of Neptune. It's odd. So you've got Jupiter with Neptune orbiting around it. And even weirder, the orbit's tilted in such an odd way that every so often, sometimes the eclipse, the Neptune moon doesn't pass in front of the star. So that's why we're missing. Every so often the eclipse misses this object. So it's weird. Anyway, so we've got a Neptune-sized moon, which is odd, but we'd expect to see a big fat moon first of all. So kind of, that's okay. Then somebody on the internet, one of the astronomers I follow, said, ha, you know what, I bet you can have a moon as well. And it turns out you can. So the moon can have a moon. And then people were saying, well, okay, what do you call it? Because there's no proper name for it. Moon, and it was meant as a joke, but an awful lot of people took it seriously. Like, you just can't name it that. It's like, we were joking. Honestly, we were just having a laugh. Like, what do you call a moon of a moon? But it turns out, dynamically, this is doable. There could be an Earth-sized mass moon orbiting around the moon, so it would be an Earth-moon. Completely wrong. So you can have a look. There's Sean Raymond who was looking about it. And basically, you can have something series-sized, 1,000 kilometre cross moon orbiting around. And maybe, if the conditions are right, if it's in the habitable zone, you could have a habitable sub-moon system. This is brilliant. You know, nobody, when I was growing up, never expected anything like this in my life, and it's just brilliant to see it actually happen, all these completely bonkers discoveries. Okay, so David went off and did that, didn't get any moons. Method number 2. So the way we think moons and planets form is, this is our picture. So stars form from a big cloud of dust and gas. Gravity pulls it together, makes the star, and makes a disk of material orbiting around the star, circumstellar disk. Planets form from little seeds orbiting around this disk, and you get a thing called a circumplanetary disk. What happens after a while is the star switches on, and all the materials from the circumstellar disk gets blown away. It leaves this circumplanetary disk. Then the circumplanetary disk starts forming moons, and it carves out tracks in this circumplanetary disk, and eventually that dust gets blown away as well. So this is generally the way we think planets and moons are made. What does this have to do? Well, jump to, a friend of mine was looking for transits in a camera which was based on the ground, and his student came in and said, yeah, I looked at one of the stars you told me to look at and it looks weird. And he says, well, how is weird? Yeah, what do you mean weird? And he says, well, the star switches off. What? So this is time in Julian days. So this is about 10 years worth of data from telescopes on the ground, small telescopes on the ground, and this is a very young star. If the sun is my age, this would be about a 2-month-old baby, and that's where we expect planets to form. So let's have a look at this light curve. And I apologise, I know half of you know full well what magnitudes are, but for the people who don't do astronomy, magnitudes are how we measure the brightness of a star. And what you're seeing here is this star is changing in brightness, and over about 2 months. For 2 months, it's as if my daughter ran up to the light switch and started flickering it on and off vigorously, right? And if we then look at the night-to-night changes, it gets even more crazy. Because this star is switching on and off by 50%, its brightness is changing by a factor of 2 over about 4 hours. That's completely bonkers. The star's a big thing, it's hot and burning and you don't want to touch it, and how do you switch it off for a while? Very difficult. So, and it's even weird, so it's just changing its light like this, and then it's been fine ever since. So what we think we've got, and I did some of the work on this, is we think we're seeing one of those giant ring systems. We think we've seen a circumplanetary disk, all the material orbiting around that planet, and it's forming moons right now. We've caught it at just the right time to spot this. And it turns out this ring system is huge. It can be very, very big indeed. And I say that we're seeing the rings move in front of the star. Just to get an idea of how big this is, most people are used to the rings of Saturn. Now there's a magical distance from Saturn called the Roche radius. And basically, the rings of Saturn are not solid. They're made of lots of separate blocks of ice. And depending on the distance from Saturn, those blocks of ice travel around at different speeds. So if I was sitting in the middle of the rings there, all the blocks of ice on the inside, close to Saturn, will be whizzing past me and running around faster, just like people on a racetrack during a race. And all the stuff on the outside I'm overtaking. That difference in speed prevents gravity from making moons, big moons in the rings of Saturn. That's why they've lived forever. The rings are always sitting there. But the ring system which we thought was going on is much, 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 much bigger than the Roche radius. So it turns out there's another magic radius called the Hill radius. So the Hill radius is if you put a blob of material within the Hill radius, it orbits around the planet. If you put the blob of material outside the Hill radius, it orbits around the star. And it turns out the ring system that we came up with sort of just squeaks in the Hill radius for this planet, so all well and good. And I got to play around with the computer and make animations. So this is the light curve at the bottom. That's the actual size of the star. And this was back in 2007. And the data sat on a hard drive and nobody noticed it for about 5 years. You could type in this number and you'd see this light curve, but nobody knew what to do with it. What's exciting though is we think we see a ringed gap. In this ring model, it's not perfect, but it does a reasonable job. So the orange line is hitting through all the yellow dots. But basically, if you took the rings of Saturn off and you put on the rings of J1407, this thing would be as big as your hand in the sky. It would ruin astronomy for about 6 years at a time because it would reflect so much light, it would ruin doing nighttime astronomy. Astronomers hate it for 6 years and then it goes around the other side of the sun and you can do astronomy for a while. But we think that's in there. So there's a gap in the rings and this thing is stupidly big. So this is a fancy way of, so what I did was, as an astronomer, you have to make an estimate, you have to kind of count up all the material and say, could you make a ring system this big? And it turns out, yes, it's a reasonable amount of stuff. And what I was excited about was this gap in the rings is about 60 million kilometers away, and you can work out how big, how fat a moon do you need to make in order to clear out that track, in order for gravity to win out. And it turns out it's a Mars mass exomoon. So I put this in a paper, and the referee, another scientist, came along and said, yeah, that sounds reasonable. And so we got it published and went, yeah, and it was really good. So I've been very excited by this system, but guess what? We've been following it for the past 10 years, and it's not eclipsed again. So for me, it's very frustrating, because this was in old data, right? This was in data from 12 years ago. And this thing is probably on a big orbit, so I'm kind of waiting for any day now, or any year now, this thing to move in front of the planet, in front of the star again. And then I can throw big telescopes at this. We can measure the composition, we can tell you what stuff the rings are made out of. So I'm very excited about it, but I'm sitting on my hands waiting. But you can go onto this website, avso.org. There are astronomers who take pictures every night for me, and I thank them from the bottom of my heart. And they're following it. They're just waiting for that big dip to happen again. So that's another way of finding ring systems. So, what's interesting with this, so these are the gaps every year. So this is 1, 2, 3, 4, 5, 6. We're in the 6th year of following this. And then you can't see it because the sun blocks it. The sun gets in the way for a few weeks. Anyway, I'm very excited about this. I'm trying to find other exo-ring systems around other stars, but it's kind of tricky because astronomers are saying, you want to find what now? Each time I tell them about this big ring system, all the astronomers look at me like I'm going crazy. But what's great is they can't think of a better explanation. So it's the best thing ever. It's if you get other people go, oh, that can't be right. Like, right, explain it any other way. And they go, yeah, okay, you're right this time, but I'm waiting for them to prove me wrong. And then I'll move on to something. Anyway, so there's a third way which I want to talk about for looking for exomoons. And I think this is another really cool, somebody thought out of the box about this. So this is a picture of Io in visible light. So this is one of the Galilean moons orbiting around Jupiter. On the right is a picture taken at about 4 microns wavelength. So that's where, all of us and the Earth radiates. We glow very brightly at 4 and 5 and 10 microns, at a much longer wavelength. So visible light is about half a micron. Infrared light is about 10 times the size, and it's very sensitive to hotspots and heat. And what you can see here in this picture on the right are volcanoes. Io is volcanic. It has sulfur volcanoes, and they're firing off all the time. So they're named after Loki and Ragnarok and stuff from Viking mythology. And this is a picture taken with the Juno camera which flew out to Jupiter. There's a whole set of volcanoes just popping off all the time. So what is making Io volcanic? That's crazy. If you do the calculation, it should have turned into a lump of very cold rock with lots of craters on the surface. And Io keeps on replenishing its surface once every 100 years. The whole thing just goes liquid and gets re-plastered with all these power flows. So, multiple moons is the key. So it turns out the Galilean moons of Jupiter are in a special configuration called resonance, called Laplace resonance. So the innermost moon is Io, and what happens is that the next two moons out, so the innermost moon Io goes round once, the next moon out goes round twice, and the next moon out, Io goes round twice for each time that Europa goes round once, and for Ganymede it's 4 times. So every so often all of them align up. And what happens is that because of this resonance, it's just like in the playground when you push a child, or me, on a swing, and it's just pushing the moons at the right time, and so you get tidal forces. So just like the sea goes up and down, there's a more extreme version of tides which are happening with Io. Io is being squeezed all the time by these tidal forces, and it has been so for giga-years. And we can see it as well. So in Europa, it's covered with a shell of ice. All these cracks are due to the stresses of tidal stresses. So the ice breaks open, material seeps up from beneath, splashes out on the surface, turns red, and you've got hundreds of thousands of these cracks, and we can tell that they're from this tidal stress heating. So we think the same thing happens with exomoon systems. So what's happening in the next couple of years is that this telescope will be launched. It's the James Webb Space Telescope. It's a 6.5 meter telescope, and it's designed for looking for that thermal heat, that long wavelength radiation. And it's going to be used for a huge amount of astronomy. We're going to look at the most distant galaxies in the universe, going to understand the nature of rotating stars, also look for exoplanets, transit. And what happened was that a graduate student called Marianne Peters and her supervisor said, well, hold on a minute. If there are moons around other planets and they're in this same special configuration, those super-Earths will get squeezed by those tidal forces and they'll heat up. And we can actually see them, so they're called tidally heated exomoons. So for the closest stars and the closest planets, we'll be in the weird situation. So what this is the wavelength of light you're looking at. So 10 microns and 4 microns was where we saw before here. Those two lines at the top are how bright the sun is and how bright is the smaller star. And basically these curves here are a tidally heated super-Earth as an exomoon. It's being squeezed all the time. And it turns out, for the James Webb Telescope, we can just about do it. So we think we can detect tidally heated exomoons, Peters and Turner think that they can detect these moons, and I agree with them. I think this is going to be a really cool project. And now I have to write a proposal to convince the JWST people to give me time to go and look at this, or Peters and Turner will go off and do it as well. Several people are looking at this. So this is a third way of detecting exomoons. Okay, so basically what's next? We've got one potential candidate with the Kepler system, which David and Alex are looking at. What we have now are 2 other satellites. We've got one which just got launched last year called TESS, and this is doing far more light curves than Kepler did, but they're looking at lots and lots of nearby systems. They're trying to get transiting super-Earths, and I'm sure that people will look at transit timing variations to see if there are exomoons with the TESS data. And you can go off now if you want, and you can download this data yourself. It's being released very quickly, and you can go off and look for planets in the data, and a lot of astronomers, it's like having a tremendous race. They're trying to, who's the fastest on the keyboard to find a planet in the test data. And Plato is another mission which will come along in a few years. The Hubble Space Telescope is being used to look at Kepler 1625. I believe there's another transit coming up in May this year, and they're going to be following this and see if they see that weird kind of shoulder pattern again, and hopefully confirm it as an exomoon, a very weird big exomoon. I'm trying to find more ring systems with 1 and 2 very, very patient students who are listening to me babble on about this and saying we can find more ring systems. And finally, the third method is JWST imaging for these tidally heated exomoons. So I think the future is quite bright for finding exomoons. It's going to be challenging, but it always was. If it was easy, it would be on Wikipedia. So we're going to be hunting over the next 10 years, and I think we'll be starting to detect many, many more of these systems, and maybe hundreds of exomoons if everything works out well in the end. And with that, I'd say thank you very much.
Thank you for your talk. Very interesting. With the line curve of Kepler 1625, there were 2 shoulders. So I didn't expect that if the moon was leaving. It's well, you can suppose that there's a ring system then if it's on both sides. Right?
So what happened? I think for the 2 shoulders case.
Yeah. This one, yeah.
This one.
The bottom.
Okay, right. I think, if I remember the geometry correctly, I have it. So, the moon starts crossing first, which gives that first bit of the shoulder. The planet starts crossing, and the moon's orbited during the transit. So yeah, it takes 24 hours for the planet to move in front of the star during that time.
Okay, but what would it look like if Saturn transited the sun? Wouldn't it look the same?
So no, because these big shoulders are because the moon is a relatively long way away from the star, from the planet, and the rings. And if you make rings around the planet, they've got to be fairly close in. So Saturn's rings are really tight. So what happens is that Saturn makes a tiny, tiny change here and here, and you don't get those big shoulders. But yes, people have looked for that as well. So they've looked through all the Kepler data, and they're trying to find Saturn transiting planets as well. And there's nothing convincing at the moment. It's really frustrating. There are a couple of light curves where people, if you squint at it and go, maybe it could be a transiting Saturn. The trouble is you have to wait 10 or 12 years for the planet to come around again and transit. Yeah. And you better be sure you've got your timing right, because if you're off by a day, you've got to wait another 12 years. So it's a game of patience. So you do it by looking at many tens of thousands of stars and hope you get lucky and catch it in the end.
Yeah, so I'm actually not an astronomer, so I'm trying to figure out, you observe the light curves around the stars, and you see a particular transit.
Yeah.
How do you find out that this transit is by a certain planet? I can assume that it must be the characteristic of the dip in the intensity.
So it's a dip and it repeats. So Kepler said you have to see 3 transits in a row. Just one dip isn't good enough. It could be anything floating in space moving in front of it.
Right.
In front of the star. Or the star could have done something weird for those few hours. So what it is the repeating. So you see 3 transits and they're equally spaced in time. So that's kind of the gold standard.
Those timings are not usually affected enough. Like, for example, you showed that because of the moons,
yes,
the timing might not be exactly the same.
Correct.
It might go up and down by some.
So for an exomoon, it's a difference of seconds. Okay, they have to measure. So the transit lasts several hours, and your timing transit is a few seconds earlier or a few seconds later. It's an incredibly difficult measurement to make, but you can do it. It's doable. Sure.
You can only see things if it's in the line of sight.
Yes.
Is that the distribution? Is that just randomly, or is it something like a collector plane?
No, it's totally random. So you take a big pile of hula hoops, throw them up in the air and take a photo before they come crashing down on you. That's the distribution of orbits of planets around stars. You know, if you take the photo and look at the photo, only a few of the hula hoops are edge on. But you're missing 90% of the hula hoops, which are at different angles. So the lower limit for Kepler is 2,000 planets, but you can multiply that by 10 at least. Okay? So there's at least, if Kepler's seeing 2,000 planets, there are at least 30,000 to 50,000 planets we're not seeing because the orbits are tilted off. And there's nothing magic about the Earth. We're a random point in the galaxy, take a photo. You know, if somebody stands over there and photographs me throwing hula hoops, they'll see a different set of hula hoops edge on from the ones I see. And it's just, you can work out the numbers. Yeah. Do it in the computer instead of taking photos of hula hoops. Hurt your head less.
You said Kepler 1625b wasn't visible for 3 weeks a year because the sun was in front. Could that transit happen?
For 1625b, you can see it at any time from the Hubble Space Telescope. I can't remember whether there's sometimes you can't see it because the sun gets in the way and the Hubble Space Telescope is not allowed to point near the sun. But I think the next transit is sometime this year. And I know they're definitely going to look for the transit again and see what happens.
Okay, so you won't miss it if it's there?
No, they know enough to know exactly when to point the Hubble Space Telescope and press the go button
That's fine.
on the camera. But the trick is, they don't know, there are several different possible orbits of the exomoon around the planet, and you don't know which one's the correct orbit. So you just got to take the data and hope it looks like a positive signal. But they, just to be very clear, they've done an amazing job on extracting that signal. And it's very, very easy. The easiest person to fool is yourself. And I've done it to myself a couple of times and thankfully wasn't too stupid about it. But they have been so professional about it, it's amazing. Like each time I read their paper, oh, it's going to be wrong, it's going to be wrong. Each time I went, oh, they didn't think of this effect. Oh, yeah, they did. And it doesn't matter. Oh, what about this effect? Oh, yeah, they've done that. But, okay, very nice job. You know, they were incredibly thorough, so they know exactly what they're doing. And I've got my fingers crossed for that, because that would be really good. And it's weird. It's like Neptune around Jupiter. Who ordered that? I mean, it's nuts.
For life, you still need to know the temperature and the presence of water, isn't it?
Yes, so the temperature is a relatively easy one to do. There's a simple formula which says how bright is the star, how far are you away from the star, what's the equilibrium temperature on the surface. Whether there's water on there or not, that's the 10 million euro question. Right? So, to look for water, you can either see it as a gas and do transmission spectroscopy. You can see water absorption features when the planet transits. What I'm interested in is if it's covered in ocean and it's not too cloudy, you can see the glint of the sunlight off the ocean because it's a polarized signal. So polarization is a particular property of light. The light from the star is unpolarized, but when it bounces off the ocean and towards the Earth, the light becomes strongly polarized when it reflects off the surface of an ocean. So that's why Polaroid sunglasses work. They're throwing away, the light's bounced off the road and it's polarized, and you can get rid of that for glare production. But that's a ridiculously tiny signal. But it's something we're looking for, right? You know, you don't know if you don't look, and with the next generation of super big telescopes, we think we can do it. You know, Kepler's told us, pick 5 stars in the sky tonight, one of them will have a rocky planet. That's a staggering statistic to come up with, right? Just look up tonight now, when it's clear. Yeah, a good fraction of the stars that you see with your naked eye have rocky planets in orbit around them. That's a staggering statistic, which we didn't know 20 years ago. I had no idea. So it's changed the way NASA thinks about missions. Before, they had to build a very complicated satellite which had to look at lots and lots of different stars. Now the answer is, well, pick your 10 favourite stars and go and look at them. And it makes the mission slightly simpler. Because you don't have to worry about looking at 100 stars for a rocky planet, you only do it for 10 or something.
I think instead of less simple, you mean less difficult.
Yes, I say less difficult. It's still incredibly difficult for different reasons. That's why. Yes.
Thanks for the talk, by the way. And you've shown a very interesting view graph with the wavelength coverage of future instruments.
Yes.
Space telescopes. And there was also the thermal infrared, or the far infrared, I would call it, at 50 micrometers. And there's also absorption features actually from molecules like CO2, water vapor.
Absolutely, so ozone absorption, stuff at 10 microns and whatever have you.
Are you aware of any spectroscopy mission there? Because I think the James Webb will only take pictures in the broadband pictures in that region, or are they
No,
doing...
it goes out to 25 microns, but I'm trying desperately to remember what's the longest wavelength it does a spectrograph at. It's certainly 10.
So then would you expect that they could even then detect spectral features from such molecules, and ozone would be, of course, spectacular.
Sure. So what they're hoping to do is that they'll detect it by the planet moving in front of the star, and you see the changes. What you can do is you can basically measure the size of the planet at different wavelengths. And if you do that for some stars, then the planet looks bigger. And it's not because the planet's bigger, it's because there's a gas on the surface, in the atmosphere of the planet, and that's blocking a bit of light. So if you look at the Earth, we have beautiful blue skies. Okay, the Earth looks bigger in blue light than red light, because the blue light's being bounced all around the place. So an alien a long way away would look back at the Earth, and if we were transiting, it would be able to work out there's oxygen in our atmosphere quite easily. They'd also see a huge amount of CO2 all the time. There's a whole load of indicators that you can do, and that's what we hope to do in the same. We want to put up satellites. I'm not sure what the longest wavelength of JWST for spectroscopy is. I need to look that up.
For this system 1625b, we showed that the disk of gas around the planet, where the moon is orbiting, for example, and plates are present, that was off the ecliptic by a particular angle.
Sure, yes, so it's all tilted.
Yeah, do you know why that might be? Do you think it's because it's a young star and it's still...
No, not really, to be honest. So, but if you look around the solar system, Saturn is 22 degrees off, Uranus is 98 degrees off, Venus is going around the wrong way. Okay, so 2 out of the 8 planets in our solar system have clearly had something really honking big hit them and tilt them over. So when they're initially made, they're probably coplanar.
Right.
But the early solar system is a violent and nasty place, and things get knocked off true. And so I don't know why it's tilted off, but seeing something tilted off shouldn't be that surprising. Given, look around the solar system, things are knocked off a little bit. One back and then,
I'm not from an astronomy background, so this may be a silly question. Is it possible to have a binary planet system?
No, that's a great question. No, so can you have binary planet system? Yeah,
the third graph, doesn't that correspond to a binary planet system where they have a center of mass? Initially, one planet is in front of the star, so there's a small dip, just show you. So I was wondering whether it should be a moon as big as planet, or can it be a binary star system?
I think the definition of if it's a binary planet system is if the center of mass is outside the surface of both. For this one, I'm afraid I'd have to look at the paper, I can't remember. I think the the center of mass is inside the Jupiter, is inside the bigger planet. So it's technically a moon, but that's a ridiculously big moon. It's odd. Okay, one of the big issues they had was nobody was expecting this. But 20 years ago, we weren't expecting big fat planets in 3-day orbits around their stars, right? Nobody thought of it. Because how do you get a big fat planet? You make them far away. Something pushes them in and leaves them there right next to the star. And so they're probably bad places for life. Because you probably had something like the Earth, this big fat planet migrates in, moves in, and just swoops everything else out of the way. And it's scattered out. And in fact, one of the more uncomfortable things that it points out with the exomoon thing is, since we're seeing no exomoons with Kipping's work, there must be a whole load of moons which get scattered. Right? The moons just get ejected out of their stellar system, and they don't disappear, they're floating around there somewhere. But space is really big, so we wouldn't see it. But it's kind of unnerving, drifting off in the galaxy. If you ever saw Space 1999, which is a science fiction series, that happens right now. It really happens. The moon's just tootling off into interstellar space.
After the work of and the discoveries with Kepler, do we have a good estimation for the number of rocky planets or Earth-like planets around solar-like or sun-like stars in the habitable zone in the galaxy?
We do, and I'm totally blanking on the exact number. So for rocky exoplanets at any radius, it's 1 in 5, I believe, is the number. But specifically in the habitable zone, I'm afraid I can't remember the number offhand. I think it's 5% or 1%.
Of all stars?
Of all solar type stars. I've got to be careful because there are tiny stars and there are big stars, and solar type stars, I think the number is 1%. And it's good. I mean, 200,000 million stars in our galaxy. Okay, so it's only 2,000 million planets in our galaxy. There are a lot of planets out there. We're not unusual, which is kind of good.
Any questions? Okay, then I'm going to thank you very much for this very interesting lecture. I really enjoyed it. Waiting for the next transit of the ring system.
Absolutely. Me too.
First of all, some beautiful flowers. And then we have it's a kind of tradition for the spring lectures. We always get a mug with all the lectures of this year.
Oh, wonderful. Thank you very much.
So this one's also for you. And our special gift for this year is Apollo 11 50 years.
Oh, awesome. Wow. Thank you very much. Thank you. Thank you for your patience.
And for all of you, if you still have enough of hearing more about our moon and other moons, next week we have one more lecture in this series. It will be given by James Carpenter from ESA about our future lunar explorations. And that's for next week. It will also be given in English, so it will be interesting for all of you. So for now, we all can go back downstairs for some coffee and tea in a moment. And for all of you who already have a ticket for a tour, the tour starts at 3:15. And if some of you don't have a ticket but still want to join, you can buy a ticket. Okay, that's it for now.